Picture this. Two particles, created together in a laboratory, are separated by thousands of miles. One is measured in Tokyo, the other in New York. The instant, and I mean the exact instant, the Tokyo particle is observed, its partner in New York responds. Not after light has had time to travel between them, not through any known signal or force, instantaneously. This isn't science fiction. This is quantum entanglement, and it's so strange that Albert Einstein himself couldn't accept it, dismissing it as spooky action at a distance. Welcome to one of the most profound mysteries in all of physics, a phenomenon so counterintuitive that it challenges everything we think we know about reality, causation, and the very nature of existence itself. I'm here to guide you through this gentle exploration of quantum entanglement, where we'll discover why Einstein was so disturbed by this phenomenon, how modern experiments have proven him beautifully wrong, and what this means for our understanding of the universe we call home. Whether you're settling in for the evening or taking a quiet moment to expand your mind, let this be a space where wonder and understanding can peacefully coexist. Before we dive deeper, I should mention that everything we'll explore tonight is grounded in rigorous scientific observation and mathematical precision. While the implications may seem almost mystical, quantum entanglement is as real and measurable as gravity or electromagnetism. We'll walk through the actual experiments, meet the brilliant minds who uncovered these secrets, and explore what this strange quantum behavior might mean for technologies already emerging in our world. So settle back, let your thoughts slow to the rhythm of discovery, and prepare to encounter one of nature's most elegant puzzles. By the end of our journey together, you'll understand not just what quantum entanglement is, but why it represents one of the most beautiful and unsettling truths about the fabric of reality itself. Our story begins in 1935, in the midst of one of the greatest intellectual battles in the history of science. On one side stood Albert Einstein, the man who had already revolutionized our understanding of space, time, and gravity. On the other was Niels Bohr, the Danish physicist who had helped birth the strange new science of quantum mechanics. Their disagreement wasn't about mathematics or experimental results. Both men agreed the equations worked perfectly. Their battle was about something far more fundamental: the nature of reality itself. Einstein had spent his life searching for what he called the Old One, his poetic name for the underlying order he believed governed the universe. To Einstein, the cosmos was like an intricate clockwork mechanism where every effect had a definite cause, where objects had real properties whether anyone was looking or not, and where nothing could influence anything else faster than the speed of light. This wasn't just scientific preference, it was Einstein's deepest philosophical conviction about how existence itself must operate. But quantum mechanics suggested something far stranger. According to the new theory, particles didn't have definite properties until they were measured. They existed in what physicists called superposition, simultaneously possessing multiple contradictory states until the moment of observation collapsed them into a single reality. Even more troubling, when two particles became entangled, measuring one would instantly determine the properties of the other. Regardless of the distance between them, Einstein found this notion not just wrong, but absurd. In collaboration with Boris Podolsky and Nathan Rosen, he crafted what became known as the EPR paradox, a thought experiment designed to expose what he saw as the fundamental flaw in quantum theory. Their argument was elegantly simple. If quantum mechanics required instantaneous influences between distant objects, then either the theory was incomplete, or the universe operated in ways that violated everything physics had taught us about locality and causation. As you contemplate this historic disagreement, notice how it touches something deep in your own experience of reality. When you close your eyes, does the room around you cease to exist? When you think of a distant friend, that feeling of connection remains purely psychological rather than physical, yet the intuition behind it echoes the discomfort Einstein felt. Einstein's discomfort with quantum entanglement wasn't just academic, it challenged the very foundations of how we intuitively believe the world works. Einstein's criticism wasn't merely theoretical. He proposed that quantum mechanics must be incomplete, that there existed hidden variables, unknown properties that particles possessed all along, like secret instructions that determine how they would behave when measured. In this view, entangled particles weren't mysteriously communicating. They were simply following predetermined scripts written at the moment of their creation. This hidden variable theory preserved everything Einstein held dear about reality. Particles would have definite properties independent of observation. No information would travel faster than light. The universe would remain fundamentally logical and local, with each region of space influenced only by its immediate surroundings. It was a beautiful, intuitive picture that aligned with our everyday experience of cause and effect. But beauty and intuition, as we'll discover, are not always reliable guides to truth. The debate between Einstein and Bohr wasn't just about particles and measurements. It was about whether the universe operates according to what philosophers call local realism. Local realism combines two seemingly reasonable assumptions: locality, the idea that objects are only directly influenced by their immediate environment, and realism, the belief that objects have definite properties independent of observation. These principles feel so fundamental that questioning them seems almost absurd. Yet quantum entanglement challenges both simultaneously. When we say two particles are entangled, we mean they share a quantum state so completely that measuring one instantly affects the other, regardless of spatial separation. This appears to violate locality. Moreover, before measurement, the particles don't seem to possess the definite properties we observe afterward, challenging our notion of realism. Einstein's genius was in recognizing that these implications were so radical, they demanded extraordinary evidence. He wasn't simply being stubborn or conservative, he was applying the kind of rigorous skepticism that had served physics well for centuries. After all, the history of science is filled with theories that seemed mathematically elegant, but ultimately failed to describe reality. What Einstein couldn't have anticipated was that future experiments would not only test his objections, but provide that extraordinary evidence he demanded. The story of how scientists proved Einstein wrong, while simultaneously honouring his demand for experimental rigour, is one of the most beautiful chapters in the history of physics. The philosophical implications of this debate extend far beyond physics. If Einstein was correct, we live in a universe where everything has definite properties and influences travel at finite speeds. A cosmos that operates according to rules we can intuitively understand. If quantum mechanics was right, reality itself might be far stranger, more interconnected, and more shaped by the act of measurement in the scientific sense than we ever imagined. Take a moment to consider which universe feels more comfortable to you. Do you prefer Einstein's clockwork cosmos, where every effect has a local cause and reality exists independently of our awareness? Or does something in you resonate with the quantum vision of a universe, where measurement reveals properties rather than uncovering pre-existing ones, and distant objects remain mysteriously connected? To truly understand what disturbed Einstein so deeply, we need to enter the mathematical heart of quantum entanglement. Don't worry, we won't get lost in equations. Instead, think of mathematics as a language that allows us to describe phenomena too subtle for ordinary words, like trying to capture the colour of music or the texture of moonlight. When two particles become entangled, quantum mechanics describes them using what physicists call a wave function, a mathematical object that contains all possible information about the system. But here's where things become strange. This wave function cannot be separated into individual descriptions of each particle. Instead, it describes both particles as a single, indivisible quantum system. Imagine trying to describe a dance where two partners move in perfect synchronization. You could attempt to describe each dancer separately, but you'd miss the essential element, their coordination. In quantum entanglement, this coordination is so complete that the particles lose their individual identities entirely. They become, in a very real sense, parts of a single entity stretched across space. This mathematical unity has profound implications. When we measure one particle and find it spinning clockwise, quantum mechanics tells us that its entangled partner will instantly be found spinning counterclockwise. Not because it was spinning that way all along, but because the measurement of one particle forces the entire system to choose a definite configuration. The particles don't communicate, they simply share a reality so completely that measuring part of it determines the whole. Einstein found this notion deeply troubling because it seemed to require what he called spooky action at a distance. If measuring a particle in Tokyo instantly determines the properties of its partner in New York, how does the New York particle know what happened in Tokyo? What kind of signal or influence could travel instantaneously across thousands of miles? Einstein's preferred explanation was that no signal travelled at all. Instead, he proposed that the particles carried hidden instructions, like sealed envelopes containing predetermined responses to any possible measurement. When scientists in Tokyo measured their particle, they weren't causing anything to happen in New York. They were simply revealing information that had been encoded in both particles from the moment of their creation. This hidden variable theory was elegant and intuitive. It preserved locality by eliminating any need for instantaneous communication. It preserved realism by giving particles definite properties at all times. Most importantly, it restored the kind of deterministic causation that had guided physics since Newton. But mathematics is unforgiving. If Einstein's hidden variables existed, they would have to satisfy certain statistical constraints when particles were measured along different axes. These constraints, first worked out by physicist John Bell in the 1960s, became known as Bell inequalities. They represent the maximum degree of correlation that local hidden variables could produce between measurements on entangled particles. Quantum mechanics, however, predicts correlations that violate these inequalities under specific conditions. This violation isn't subtle, it's dramatic and measurable. If experiments could show that entangled particles violate Bell inequalities, it would prove that either locality or realism, or both, must be abandoned. As you absorb this profound implication, consider what it means for your own experience of reality. We're not talking about abstract philosophical speculation, but about the fundamental nature of existence itself. The mathematics was telling us that the universe might operate in ways that challenge our deepest assumptions about how things can influence each other across space and time. The beauty of Bell's work was that it transformed a philosophical debate into an experimental question. No longer would physicists need to argue about interpretations and preferences. Nature herself would provide the answer through direct measurement. The stage was set for what would become one of the most important series of experiments in the history of science. But before we explore those groundbreaking experiments, it's worth pausing to appreciate the profound elegance of this moment in physics. Here was a situation where pure mathematical reasoning had led to predictions about the fundamental nature of reality. Predictions so counterintuitive that they seemed almost impossible to believe, yet so precise that they could be tested with extraordinary accuracy. The tension between Einstein's intuitive picture and quantum mechanics' mathematical predictions created what scientists call a crucial experiment, a test whose outcome would definitively resolve a fundamental question about nature. These moments are rare in science, and when they occur, they often reshape our understanding of existence itself. Science is ultimately about testing our ideas against the unforgiving tribunal of nature, and quantum entanglement presented experimenters with an extraordinary challenge. How do you test whether reality itself operates according to principles that seem to defy common sense? How do you measure something as subtle as the instantaneous correlation between particles separated by vast distances? The first attempts in the 1970s were ingenious but imperfect. Physicists managed to create entangled particles and measure their properties, finding correlations that matched quantum mechanical predictions. But Einstein's supporters could always point to potential loopholes, ways that local hidden variables might still explain the results without requiring spooky action at a distance. Enter Alain Aspect, a French physicist whose name would become synonymous with one of the most beautiful and decisive experiments in the history of science. Working in the early 1980s, Aspect recognized that previous experiments suffered from a critical flaw. The measurement settings were determined in advance, potentially allowing hidden variables to prepare appropriate responses. Aspect's stroke of genius was to change the measurement settings while the entangled photons were already in flight. Using rapidly switching devices operating in mere nanoseconds, he ensured that the choice of how to measure one photon was made after both photons had left their source, but before they reached the detectors. This eliminated any possibility that conventional signals could coordinate the particles' responses. The setup itself was a marvel of precision engineering aspect, and his team created pairs of entangled photons by exciting calcium atoms with lasers. These photons flew apart at the speed of light toward detectors placed meters away, but during their brief journey, acoustic switches would randomly redirect them to different polarization analyzers, ensuring that the measurement choice remained undetermined until the last possible moment. When the results came in, they were unambiguous. The correlations between the photons violated Bell inequalities by amounts far exceeding any possibility of experimental error. Nature had spoken clearly. Einstein's local hidden variables could not explain the observed phenomena. Reality itself appeared to operate through genuinely non-local connections. Non-local in the quantum mechanical sense, without involving faster-than-light signals. As you contemplate the implications of Aspect's experiment, consider the remarkable chain of reasoning that led to this moment. Pure mathematical theory had predicted that reality might operate in seemingly impossible ways. Brilliant experimenters had then devised techniques to test these predictions with extraordinary precision, and nature had revealed herself to be even stranger and more wonderful than our everyday experience suggests. The beauty of Aspect's work wasn't just in its technical excellence, but in how it resolved a fundamental question about the nature of existence. For nearly half a century, physicists had debated whether the universe operated according to Einstein's intuitive local realism or quantum mechanics' bizarre non-local correlations. Aspect's experiment provided a definitive answer. The universe is indeed non-local in ways that Einstein found deeply troubling. Though this non-locality does not permit communication or information transfer beyond the speed of light. But what does non-local actually mean? It doesn't mean that information travels faster than light, or that we can use entanglement to send messages instantaneously. Instead, it suggests that reality itself has a kind of wholeness that transcends our usual notions of spatial separation. Entangled particles don't communicate, they participate in a shared reality that cannot be decomposed into separate, independent parts. This non-locality is perhaps easier to understand through analogy. Imagine two dancers who have rehearsed together so extensively that they can perform in perfect synchronization even when separated by a great distance. To an observer, it might appear that they're communicating instantaneously, but in reality, they're both drawing from a shared choreography that exists beyond either individual dancer. Similarly, entangled particles share a quantum choreography that exists at a level deeper than individual properties or locations. Measuring one particle doesn't send a signal to its partner. It reveals an aspect of their shared quantum reality that was already present but previously unmanifested. The philosophical implications of Aspect's results continue to reverberate through physics and beyond. If reality is fundamentally non-local, what does this mean for our understanding of space, time, and causation? How should we think about the relationships between parts and wholes, between individual objects and the systems they comprise? These questions don't have easy answers, but they remind us that science is ultimately about expanding our conception of what's possible. Aspect's experiment didn't just confirm quantum mechanics, it revealed that the universe is far more subtle, interconnected, and mysterious than even Einstein imagined. One of the most striking aspects of quantum entanglement is its apparent instantaneity. When we measure an entangled particle and find it spinning in a particular direction, its distant partner immediately responds with the complementary spin. This correlation appears to occur faster than light could travel between the particles, a phenomenon that would seem to violate one of Einstein's most cherished principles. Einstein's special theory of relativity established that nothing can travel through space faster than light. This isn't just a practical limitation, it's a fundamental constraint that preserves causality itself. If information could travel faster than light, it would be possible to send messages into the past, creating logical paradoxes that would undermine the rational structure of reality. Yet quantum entanglement seems to mock this speed limit. Modern experiments have confirmed correlations between entangled particles separated by distances that would take light significant time to traverse. In 1998, researchers in Geneva demonstrated entanglement between detectors separated by 30 kilometers using Switzerland's optical fiber network. If some kind of signal were coordinating the particles' responses, it would have to travel at least 10 million times faster than light. A possibility ruled out, because quantum correlations do not carry usable information. Even more remarkably, recent experiments have pushed these distances to truly astronomical scales. Scientists have successfully demonstrated entanglement between ground-based facilities and satellites orbiting hundreds of kilometers above Earth. The correlations remain instantaneous regardless of the growing distance, suggesting that whatever connects entangled particles operates outside our normal understanding of space and time, while still obeying the no communication limits of relativity. But here's where the story becomes even more fascinating. Despite these apparently faster than light correlations, quantum entanglement cannot be used to transmit information or violate causality. This seeming contradiction lies at the heart of what makes quantum mechanics so profoundly strange, and yet ultimately consistent with relativity. Take a moment to consider this paradox. How can two particles respond to each other instantaneously across vast distances without allowing faster-than-light communication? The answer reveals something deep about the nature of information and correlation in quantum systems. When we measure an entangled particle, we obtain a random result. If I measure my particle and find it spinning clockwise, I know instantly that yours must be spinning counterclockwise. But this knowledge doesn't allow me to send you a message. From your perspective, your measurement results appear completely random until you compare them with mine through conventional, slower-than-light communication. It's analogous to having two coins that are somehow connected, so that when one lands heads, the other always lands tails. Even though their outcomes are perfectly correlated, neither coin flip can be used to influence the other or transmit information. The correlation exists, but it cannot be exploited for communication. This distinction between correlation and communication is crucial for preserving causality while allowing for genuine quantum non-locality. The universe can be deeply interconnected in ways that transcend space and time without creating logical paradoxes or enabling science fiction scenarios like faster-than-light messaging. The implications extend far beyond physics. If reality contains correlations that operate outside the normal flow of cause and effect, what does this tell us about the nature of connection itself? How should we understand relationships, influence, and interdependence in a universe where distant events can be genuinely correlated without being causally connected? Some interpretations suggest that quantum entanglement reveals something fundamental about the structure of information in the universe. Rather than thinking of reality as composed of separate objects that occasionally interact, we might need to envision existence as a vast network of correlations, with individual particles or events emerging as local manifestations of more fundamental patterns. This perspective doesn't diminish the mystery of entanglement. If anything, it deepens it. We're not just dealing with a strange physical phenomenon, but with evidence that reality itself might be organized in ways that transcend our ordinary notions of space, time, and individual identity, all without invoking metaphysical or supernatural interpretations. As experimental techniques continue to improve, scientists are pushing the boundaries of entanglement to ever greater distances and more complex systems. Each new experiment confirms that the non-local correlations predicted by quantum mechanics are genuine features of nature, not artifacts of imperfect measurements or incomplete theories. The story of quantum entanglement isn't just about particles and mathematics. It's also deeply human, filled with brilliant minds grappling with ideas that challenged everything they thought they knew about reality. The central drama involved two of the greatest physicists who ever lived, Albert Einstein and Niels Bohr, whose intellectual battle over quantum mechanics shaped the entire trajectory of modern physics. Einstein approached physics with what we might call classical intuition elevated to genius level. His revolutionary insights about relativity had come from thought experiments that combined rigorous mathematics with deeply intuitive pictures of how space, time, and gravity must operate. He could visualize riding alongside a beam of light, or imagine how gravity might bend the fabric of space-time. This combination of mathematical precision and physical intuition had served him brilliantly in developing both special and general relativity. But quantum mechanics resisted this approach. The theory worked mathematically. Its predictions were confirmed by every experiment. Yet it painted a picture of reality that seemed to defy visualization or intuitive understanding. How could a particle exist in multiple states simultaneously? How could measurement create rather than merely reveal reality? How could distant objects remain connected in ways that transcended space and time? Bohr, by contrast, had learned to embrace the counterintuitive nature of quantum phenomena. He developed what became known as the Copenhagen interpretation, which essentially argued that quantum mechanics was complete as it stood, even if its implications seemed strange or paradoxical. According to Bohr, the act of measurement didn't reveal pre-existing properties, but actually brought those properties into existence in the technical, quantum mechanical sense, not through consciousness or intention. The philosophical divide between these giants ran deeper than physics. Einstein believed in what philosophers call objective reality, the idea that the universe has definite properties independent of our observations. To him, the moon existed whether or not anyone was looking at it, and particles had real locations and velocities even when unmeasured. Science, in Einstein's view, was about discovering the underlying order that governed this objective reality. Bohr questioned these assumptions. Perhaps he suggested the very notion of objective reality, independent of measurement, was a classical prejudice that needed to be abandoned. Maybe the universe was fundamentally relational, with properties emerging only through interactions rather than existing as intrinsic features of isolated objects. Their famous debates, conducted through scientific papers, conference presentations, and personal correspondence, weren't just about quantum mechanics. They were about the nature of knowledge, reality, and the philosophical questions surrounding observation in the physical world. Einstein would propose thought experiments designed to show that quantum mechanics led to logical contradictions or absurd conclusions. Bohr would respond by carefully analysing these scenarios and showing how quantum mechanics provided consistent, if counterintuitive, explanations. As you reflect on this historic dialogue, notice how it touches questions that extend far beyond physics. What is the relationship between mind and reality? Can we know anything about the world independent of our observations? Are there aspects of existence that transcend the categories of classical logic, questions explored in philosophy, not evidence of literal quantum effects in human awareness? The EPR paradox represented Einstein's most sophisticated attempt to demonstrate the incompleteness of quantum mechanics. By showing that the theory seemed to require instantaneous influences between distant particles, Einstein hoped to prove that quantum mechanics was missing crucial elements, the hidden variables that would restore locality and realism to physics. Bohr's response was characteristically subtle. He didn't deny that quantum mechanics implied non-local correlations. Instead, he argued that these correlations didn't constitute influences in the classical sense. According to Bohr, entangled particles shared a quantum wholeness that transcended spatial separation, but this wholeness couldn't be used to transmit information or energy between distant locations, and did not imply any role for conscious observers in causing physical effects. This exchange revealed a fundamental tension between two ways of understanding reality. Einstein's approach emphasized analysis, breaking complex systems down into constituent parts and understanding how those parts interact according to universal laws. Bohr's approach emphasized synthesis, recognizing that quantum systems possessed irreducible wholes that couldn't be understood by analyzing their components in isolation. The debate remained largely philosophical until Bell's theorem provided a way to test these competing visions experimentally. Bell showed that Einstein's local realism made specific, testable predictions about the correlations between measurements on entangled particles. If these predictions were violated, it would prove that reality operates in ways Einstein found unacceptable. When Aspect and subsequent experimenters demonstrated clear violations of Bell inequalities, they weren't just confirming quantum mechanics, they were resolving one of the deepest philosophical disputes in the history of science. The universe, it turned out, operated more like Bohr envisioned than Einstein preferred. But this resolution came with a profound irony. Einstein's demand for experimental rigor, his insistence that extraordinary claims require extraordinary evidence, had ultimately led to experiments that proved his own philosophical position wrong. His intellectual integrity had contributed to the very discoveries that challenged his deepest convictions about reality. Perhaps the most profound recognition from this historic debate is that both Einstein and Bohr were pursuing the same goal through different paths, a deeper understanding of truth itself. Einstein sought truth through the clarity of classical logic and the elegance of unified theories. Bohr found truth in accepting the inherent limitations of classical concepts when applied to quantum phenomena. Their disagreement wasn't about the quality of their commitment to science, but about the nature of reality at its most fundamental level. What emerged from their intellectual struggle was something neither man fully anticipated, a new way of thinking about the relationship between observer and observed, between knowledge and reality, between the parts and the whole. This wasn't just a victory for one interpretation over another. It was an expansion of human understanding that revealed the universe to be far richer and more mysterious than either classical or early quantum thinking had imagined. As we move deeper into the implications of quantum entanglement, we encounter questions that stretch beyond physics into the very nature of existence itself. If particles can remain connected across vast distances without any physical link between them, what does this tell us about the fundamental structure of reality? Are we living in a universe where separation is, in some sense, an illusion, in the scientific sense of relational structure, not a metaphysical one? Consider for a moment your own experience of connection. When you think deeply about a loved one far away, there's a quality to that awareness that feels immediate and present. While classical physics would tell us that no physical influence travels between you and that distant person, the emotional experience of closeness is a human psychological phenomenon, not a quantum one. Quantum entanglement doesn't prove that human connections operate through quantum effects. Such claims would be scientifically unfounded, but it does suggest that the universe itself may be more fundamentally interconnected than our everyday experience reveals in a strictly physical, not emotional or metaphysical sense. The mathematics of entanglement describes what physicists call quantum correlations, statistical relationships between measurements that cannot be explained by any classical mechanism. These correlations don't diminish with distance, don't require time for transmission, and cannot be used to send messages. They represent something genuinely new in our understanding of how reality can be organized. To appreciate the strangeness of quantum correlations, imagine two coins that have been quantum entangled. When you flip your coin and it lands heads, the other coin, whether it's in the next room or on the opposite side of the galaxy, will always land tails when flipped at precisely the same moment. This correlation is perfect and instantaneous, yet it provides no mechanism for communication between the coin holders. The correlation exists at a level deeper than the individual properties of either coin. In quantum mechanical language, the two coins don't have individual states at all until measured. Instead, they share a single quantum state that encompasses both objects as parts of an indivisible whole. Measuring one coin doesn't cause the other to adopt a complementary state. It reveals an aspect of their shared reality that was always present but previously unmanifested. This notion of quantum wholeness challenges our ordinary way of thinking about objects and relationships. In classical physics, we understand systems by analysing their components and the forces between them. A molecule is understood as atoms held together by electromagnetic forces. A solar system is planets and a star interacting through gravity. Even complex systems like weather patterns or ecosystems are ultimately reducible to interactions between discrete elements. But quantum entanglement suggests that some systems possess irreducible wholes that cannot be understood by analysing their parts in isolation. The entangled particles don't have separate identities that somehow coordinate with each other. They participate in a shared identity that transcends spatial separation. This quantum wholeness represents a form of unity that has no classical analogue. As you contemplate this idea, notice how it might resonate with your own deepest experiences of connection and belonging. While we cannot scientifically claim that human relationships operate through quantum mechanisms, the emotional sense of connectedness is understood through psychology and neuroscience, not quantum physics. The recognition that reality itself may be fundamentally relational rather than atomistic opens space for wonder about the nature of consciousness, love, and the mysterious ways we find ourselves connected to others and to the world, without implying quantum causation in human experience. Some interpretations of quantum mechanics suggest that entanglement reveals something essential about the nature of information in the universe. Rather than thinking of reality as composed of things that occasionally exchange information, we might need to envision existence as patterns of information that give rise to the appearance of separate objects and events. This informational perspective doesn't diminish the mystery of entanglement, it relocates it. Instead of asking how particles communicate across space, we might ask what kind of reality allows for patterns of information that transcend spatial and temporal boundaries. Instead of seeking mechanisms for faster-than-light influences, we might explore what it means for existence itself to be fundamentally relational in the physical, mathematical sense. This analogy isn't perfect. Quantum entanglement is more subtle and strange than any classical picture can fully capture, but it hints at the kind of conceptual shift required to appreciate what quantum mechanics is telling us about the nature of reality. The measurement process in quantum entanglement also reveals something profound about the relationships between knowledge and existence. In classical physics, gaining knowledge about a system doesn't change the system's fundamental properties. You can learn the position of a planet without affecting its orbit, or measure the mass of an object without altering its weight. But in quantum entanglement, the act of gaining knowledge appears to be intimately connected with the emergence of the properties being known. Before measurement, the entangled system exists in a state of pure potentiality. The measurement process crystallizes this potentiality into definite actualities, not just locally, but across the entire entangled system. This suggests a universe where the act of measurement, defined in physics as any interaction that extracts information, plays a fundamental role in the unfolding of reality. This doesn't mean that human consciousness creates reality through wishful thinking. Such claims would be scientifically unfounded. Rather, it suggests that the process of observation, whether by conscious beings or unconscious measuring devices, participates in the ongoing creation of definite properties from quantum indefiniteness in a strictly physical sense. As you reflect on these ideas, you might notice parallels with your own experience of how attention shapes perception. When you focus deeply on a piece of music, previously unnoticed harmonies and rhythms emerge into awareness. When you observe your own thoughts and emotions mindfully, subtle patterns and connections become apparent that were invisible during ordinary consciousness. While these experiential parallels don't prove that consciousness operates through quantum mechanisms, they do suggest that our subjective experience of observation has its own psychological significance, even though it is separate from the technical meaning of measurement in physics. The quantum world's revelation that measurement determines which outcome becomes observable within the quantum system invites us to consider philosophically, not scientifically, how our own attention might shape the world we experience. The strange properties of quantum entanglement, once confined to philosophical debates and abstract thought experiments, have begun manifesting in technologies that would have seemed like pure science fiction just decades ago. These aren't distant possibilities, but present realities emerging from research laboratories around the world, transforming our understanding of computation, communication, and the very limits of what's technologically possible. Quantum computing represents perhaps the most dramatic example of how entanglement strangeness translates into practical power. Classical computers process information using bits that exist in definite states, either 0 or 1. Every calculation, no matter how complex, ultimately reduces to manipulating these binary values through logical operations. This approach has served us remarkably well, enabling everything from smartphones to space missions. But quantum computers operate according to entirely different principles. They use quantum bits, or qubits, that can exist in superpositions of 0 and 1 simultaneously. More importantly, multiple qubits can become entangled, creating quantum states that encompass all possible combinations of values across the entire system. A classical computer with 300 bits can represent any one of 2 to the power of 300 possible states. A quantum computer with 300 entangled qubits can exist in a superposition that encompasses all 2 to the power of 300 states simultaneously. This exponential scaling represents more than a quantitative improvement. It's a qualitatively different approach to information processing. Certain problems that would take classical computers longer than the age of the universe to solve become tractable on quantum computers with sufficient numbers of entangled qubits. Factoring large numbers, simulating molecular interactions, and searching unsorted databases are just a few examples of tasks where quantum entanglement provides dramatic computational advantages. The development of practical quantum computers has required scientists to learn how to create, manipulate, and preserve entangled states under realistic conditions. This isn't merely an engineering challenge. It's required fundamental advances in our understanding of how quantum systems interact with their environments and how to protect delicate quantum correlations from the decoherence that naturally occurs when quantum systems interact with the classical world. As you contemplate the implications of quantum computing, consider how it might change not just technology, but our relationship with information itself. In a world where certain calculations become exponentially easier, which problems will we choose to solve? How might quantum-enhanced artificial intelligence systems process information in ways that transcend classical logical structures? Quantum communication represents another frontier where entanglement's properties enable capabilities impossible in classical systems. Traditional cryptography relies on mathematical problems that are difficult to solve with current computers, but these security methods become vulnerable if powerful quantum computers ever become widely available, since quantum algorithms can break many current encryption schemes. Quantum cryptography offers a fundamentally different approach to secure communication, one based on the laws of physics rather than computational complexity. By encoding information in quantum states and using entangled particles to establish secure communication channels, quantum cryptographic protocols achieve security that remains unbreakable even in principle, regardless of future advances in computing power. The security of quantum communication stems directly from the measurement-sensitive nature of quantum states. Any attempt to intercept or copy quantum-encoded information necessarily disturbs the quantum states being transmitted, immediately revealing the presence of an eavesdropper. This isn't a practical limitation that might be overcome with better technology. It's a fundamental consequence of quantum mechanics itself. Current quantum communication networks already operate over distances of hundreds of kilometers, connecting cities through quantum-secured channels. Satellites have extended these capabilities to intercontinental distances, creating the foundation for a global quantum internet that could revolutionize secure communication. But perhaps the most profound application of quantum entanglement lies in an area that sounds like pure fantasy: quantum teleportation. Despite its science fiction associations, quantum teleportation is a real phenomenon that has been demonstrated countless times in laboratories around the world. It represents one of the most elegant applications of entanglement's non-local properties. Quantum teleportation doesn't involve moving matter from one location to another. Instead, it transfers the quantum information that defines a particle's state from one location to a distant particle. The original particle loses its initial quantum state in the process, while the distant particle acquires that exact state, creating a perfect quantum copy at the destination, while the original is necessarily destroyed. The process requires a pair of entangled particles shared between the sending and receiving locations. The sender performs a special type of measurement that entangles the particle to be teleported with their half of the entangled pair. This measurement destroys the original quantum state, but generates classical information that, when transmitted to the receiver and used to manipulate their entangled particle, perfectly recreates the original quantum state at the distant location. Quantum teleportation has enabled new approaches to quantum computing, where quantum information can be moved between different parts of a quantum processor without physically transporting particles. It's also essential for quantum error correction, allowing quantum computers to detect and fix errors without destroying the quantum information being processed. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready, As these quantum technologies mature, they're beginning to reveal applications that extend far beyond computing and communication. Quantum sensors that exploit entanglement can achieve measurement precision that approaches fundamental physical limits imposed by quantum mechanics itself. These sensors are already being used to detect gravitational waves, map underground resources, and study biological systems with unprecedented sensitivity. The development of quantum technologies has also deepened our appreciation for entanglement as a resource that can be created, manipulated, stored, and consumed. Scientists have learned to think of entanglement almost like a currency that can be invested in different quantum processes to achieve various technological goals. This resource-based perspective on entanglement has opened new research directions and revealed unexpected connections between seemingly different quantum phenomena. As we've explored the experimental confirmation and technological applications of quantum entanglement, we've encountered one of the most profound questions in all of science. What does entanglement tell us about the fundamental nature of reality itself? The answer, if we're honest, is that we're still learning. Despite decades of successful experiments and practical applications, quantum entanglement continues to challenge our deepest assumptions about existence, while leaving questions of consciousness to fields like psychology, neuroscience, and philosophy. One of the most striking aspects of entanglement research is how it has consistently exceeded scientists' expectations. Each new experiment reveals that quantum correlations are more robust, more versatile, and more fundamental than previously imagined. Entanglement persists across greater distances, survives in more complex systems, and manifests in more varied forms than early quantum theory predicted. This robustness suggests that entanglement isn't merely a curious feature of microscopic particles, but represents something essential about how information and reality are organized at the deepest levels. Some physicists speculate that entanglement might be the fundamental ingredient from which space, time, and matter themselves emerge. In this view, the classical world we experience, with its apparently separate objects and local interactions, might be a kind of approximation that emerges from more fundamental quantum relationships. Consider the implications of this possibility. If space and time are not fundamental features of reality, but emergent properties of quantum entanglement networks, then our entire framework for understanding existence requires revision. Distance and duration, the basic coordinates of our experience, might be secondary phenomena arising from more primitive quantum correlations. This speculation remains unproven and highly controversial, but it illustrates how quantum entanglement has opened intellectual territories that were previously unimaginable. We're not just dealing with a strange physical phenomenon, but with evidence that reality itself might be organized according to principles that transcend our everyday categories of thought. The philosophical implications extend into questions about consciousness and observation. If quantum measurement plays a key role in determining the outcomes we observe in entangled systems, it naturally raises curiosity, but not scientific conclusions, about how observation and awareness relate to the physical world. Some interpretations explore this connection metaphorically, noting that our experience of observing the world can feel significant, while most scientific perspectives maintain that quantum measurement is triggered by physical interactions themselves, whether or not a conscious observer is present. Rather than linking quantum behavior to consciousness, these viewpoints simply highlight that the act of observation in physics has a precise technical meaning, and that our human sea of awareness is a separate, rich phenomenon, studied through neuroscience and psychology. These questions don't have clear answers, and it's important to distinguish between what quantum mechanics definitively demonstrates and what it might suggest about consciousness and reality. No scientific consensus exists regarding the role of consciousness in quantum mechanics, and claims that individual thoughts or intentions can directly influence quantum systems remain speculative and are not supported by evidence. Yet the mystery persists. Quantum entanglement reveals correlations that transcend classical notions of space and time, measurement processes that appear to participate in creating rather than merely revealing reality, and forms of wholeness that cannot be reduced to relationships between separate parts. These discoveries don't prove any particular theory of consciousness, but they do suggest that the universe is far stranger and more interconnected than classical physics ever imagined. As you reflect on these deeper mysteries, notice how they might resonate with your own most profound experiences of connection, meaning, and wonder. While we cannot scientifically claim that human consciousness operates through quantum mechanisms, our subjective sense of meaning and connection remains a powerful part of the human experience, enriched by, but not explained by, quantum physics. The study of quantum entanglement has also revealed unexpected connections between physics and information theory, suggesting that information might be more fundamental than matter or energy. In this view, particles, forces, and fields might all be different ways that information organizes itself into the patterns we experience as physical reality. This informational perspective doesn't reduce reality to mere data or computation. Information, in the quantum context, includes irreducibly qualitative aspects that cannot be captured in classical digital terms. Quantum information possesses a richness and subtlety that transcends anything achievable with classical bits and bytes. The recognition that information might be fundamental has profound implications for understanding consciousness, since consciousness is intimately connected with the processing, integration, and experience of information. While this doesn't prove that consciousness operates through quantum mechanisms, it highlights fascinating philosophical parallels while keeping scientific claims grounded in established evidence. Some researchers are exploring whether quantum information processing might occur in biological systems, particularly in the brain. While definitive evidence remains elusive, there are early scientific discussions that certain biological processes might exploit quantum effects for enhanced efficiency or capabilities. These investigations remain highly speculative, but they illustrate how quantum entanglement continues to open new research directions that blur traditional boundaries between physics, biology, and the broader study of cognition. As our exploration draws toward its conclusion, it's worth stepping back to appreciate the journey we've taken together. We began with Einstein's discomfort about spooky action at a distance, and have travelled through experimental confirmations, technological applications, and philosophical implications that reveal quantum entanglement to be one of the most profound discoveries in the history of science. What makes this discovery so remarkable isn't just its strangeness, but its accessibility. Unlike many advanced scientific concepts that require years of specialized study to appreciate, quantum entanglement touches something immediate in human experience. Our sense of connection, our intuitions about wholeness and separation, our wonder about the relationship between consciousness and reality. The mathematics may be complex and the experiments may require sophisticated equipment, but the fundamental mystery of entanglement speaks to questions that have fascinated humans throughout history. How are we connected to each other and to the world? What is the nature of reality beyond appearance? How does consciousness relate to the physical universe? Quantum entanglement doesn't answer these questions definitively, but it does suggest that the universe is far more mysterious, interconnected, and wonderful than our everyday experience reveals. In a cosmos where distant particles can share immediate correlations, where measurement determines which outcome becomes observable within the quantum system, and where wholeness transcends spatial separation, there's room for wonder about aspects of existence that classical science never imagined. This recognition invites a particular kind of intellectual humility. If nature operates according to principles that challenge our deepest intuitions about space, time, and causation, how many other aspects of reality might be far stranger than we currently imagine? What other discoveries await that will expand our understanding of what's possible in this remarkable universe we call home? Perhaps that's the greatest gift of quantum entanglement, not just new technologies or refined theories, but an expanded sense of wonder about the profound mystery in which we find ourselves immersed. In recognizing that reality transcends our classical categories of thought, we open ourselves to possibilities we hadn't previously imagined, and to forms of connection that extend far beyond anything our everyday experience reveals. As we close this gentle exploration together, take a moment to appreciate how quantum entanglement invites us into a deeper relationship with mystery itself. In a universe where the deepest truths often emerge through accepting rather than resolving paradox, perhaps our greatest discoveries await not in solving the puzzles of existence, but in learning to dance more gracefully with the questions themselves. The story of quantum entanglement continues to unfold in laboratories and theoretical investigations around the world. Each new discovery adds another layer to our understanding, while simultaneously revealing new depths of mystery. This isn't a flaw in our scientific method, but a testament to the inexhaustible richness of reality itself. And perhaps that's exactly as it should be. In a universe strange enough to allow for quantum entanglement, there's always room for more wonder, more questions, and more opportunities to expand our sense of what's possible in this extraordinary existence we share. Thank you for joining me on this journey through one of nature's most beautiful mysteries. Until we meet again in the realm of questions that expand rather than constrain our sense of wonder, may you carry with you a deepened appreciation for the profound interconnectedness that quantum entanglement reveals at the heart of reality itself. If you found yourself drawn into the mystery of how quantum effects might influence our sleeping minds, I invite you to continue this exploration with Quantum Dreams, the Hidden Code. Your subconscious is desperate to reveal, where we'll discover how the strange principles we've explored tonight might manifest in the landscape of sleep and dreams. And dreams, while quantum entanglement has revealed the profound interconnectedness that exists between particles across vast distances of space, there's another realm where similar mysteries unfold, one that's even more intimate and immediate than any physics laboratory. Every night, as you drift into sleep, your brain begins orchestrating one of the most sophisticated information processing processes in nature: the formation and integration of consciousness itself. Recent discoveries in neuroscience suggest that the brain might operate according to principles that echo, metaphorically, the strange behaviours we've explored in quantum systems. Not through literal quantum entanglement that remains highly speculative, but through organisational patterns that exhibit similar properties of coherence, correlation, and emergent wholeness that transcend simple mechanical explanations. Consider the remarkable fact that your brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. The total number of possible neural connections exceeds the number of stars in the observable universe. Yet somehow, from this astronomical complexity emerges the unified experience of being you, a single coherent consciousness that feels integrated and whole rather than fragmented into billions of separate information streams. This neural integration exhibits properties that parallel what we've learned about quantum systems. Individual neurons don't simply add up to consciousness the way bricks add up to a wall. Instead, awareness emerges from patterns of correlation and coherence that span multiple scales, from molecular interactions within cells to synchronized oscillations across entire brain regions. The whole, quite literally, becomes more than the sum of its parts. During sleep, this integration process becomes even more fascinating. As your conscious mind releases its grip on daily concerns, your brain begins a process that resembles a reorganization of classical neural networks, rather than anything quantum mechanical. Instead of quantum coherence breaking down into classical separateness, sleep appears to allow disparate neural networks to achieve new forms of integration and correlation. This isn't to say that your brain operates as a quantum computer. Current evidence suggests that the warm, noisy environment of biological tissue would quickly destroy most quantum effects. Rather, it's that the organizational principles governing consciousness might parallel those we observe in quantum systems, revealing similar themes of wholeness, correlation, and emergent properties that transcend classical mechanical descriptions. As you reflect on your own experience of consciousness, notice how it exhibits this quantum-like wholeness. Your thoughts, emotions, sensations, and memories don't feel like separate streams that happen to coincide. They feel integrated into a unified field of awareness that encompasses all aspects of your experience simultaneously. This integration occurs without any central coordinator or executive controller. It emerges naturally from the complex correlations between different aspects of neural activity. The study of consciousness and quantum mechanics has attracted considerable attention from researchers seeking to understand whether deeper connections might exist between awareness and the fundamental structure of reality. While definitive scientific consensus remains elusive, some interpretations suggest that consciousness might play a more fundamental role in the universe than classical physics ever imagined. One intriguing area of investigation involves the role of quantum effects in biological systems. While large-scale quantum entanglement is unlikely to survive in the brain's warm environment, recent research has revealed quantum phenomena in various biological processes, from photosynthesis in plants to navigation in birds to enzymatic reactions in living cells. Some researchers speculate that similar quantum-enhanced processes might occur in neural microtubules, tiny protein structures within brain cells that help maintain cellular architecture. According to this controversial hypothesis, quantum effects within microtubules might contribute to the binding of conscious experience across different brain regions. This remains highly speculative, and most neuroscientists consider classical neural mechanisms to be the primary drivers of consciousness. The brain appears to operate primarily through electrical and chemical processes that we're still working to understand fully. Yet the possibility that consciousness might interface with quantum reality in subtle ways continues to inspire research at the intersection of neuroscience, physics, and philosophy. What's particularly intriguing is how the measurement problem in quantum mechanics, the question of how definite classical properties emerge from quantum indefiniteness, parallels certain puzzles in consciousness research. Just as quantum systems exist in superposition until measured, some aspects of consciousness seem to exist in states of potentiality until focused attention brings them into definite experience. Consider your own awareness right now. Before you direct attention to the sounds around you, those auditory experiences exist in a kind of perceptual background, present but not fully actualized in conscious experience. The act of attending seems to crystallize these potential experiences into definite conscious content, much like quantum measurement crystallizes potential outcomes into definite results. A parallel used metaphorically, not literally. This parallel doesn't prove that consciousness operates through quantum mechanisms, but it suggests that similar organizational principles might govern both domains. Both quantum systems and conscious experience seem to involve the emergence of definite actualities from fields of potentiality through processes that remain mysterious despite extensive scientific investigation. Perhaps nowhere is the mysterious complexity of consciousness more vivid than in the realm of dreams. During REM sleep, the brain enters states of integration and creativity that loosen the usual constraints of waking logic and linear reasoning. Dreams blend memories, emotions, sensations, and abstract ideas with remarkable fluidity, an experience that can feel metaphorically similar to quantum superposition, even though the underlying processes arise from classical neural activity. In dreams, you can simultaneously be yourself and someone else, exist in multiple locations, experience impossible physics, and navigate narratives that shift and morph in ways that would violate classical causation. These aren't flaws or random noise in the dreaming process. They appear to be features that allow consciousness to explore connections and possibilities that remain hidden during waking awareness. Recent neuroscience research has revealed that dreaming involves a unique form of neural integration, where normally separate brain networks begin communicating in novel ways. The default mode network, associated with self-reflection and internal narrative, begins interacting with sensory processing areas, memory systems, and emotional centers in patterns rarely seen during waking consciousness. This neural reorganization during dreams creates conditions similar to what physicists observe in quantum systems approaching coherence. Normally independent neural processes become correlated and synchronized, allowing information to flow across brain regions that typically operate in relative isolation. The result is a state of consciousness that feels unified yet fantastical, coherent yet impossible. Some interpretations suggest that dreams might serve a function similar to quantum error correction, identifying and resolving inconsistencies in memory storage and emotional processing through a kind of neural annealing process. Just as quantum computers use entangled states to detect and correct computational errors, dreams might use integrated neural states to identify and resolve conflicts between different aspects of psychological experience. This remains speculative, but it points toward deeper parallels between the organizational principles governing consciousness and those observed in quantum systems. Both domains seem to involve the spontaneous emergence of coherence from complexity, the resolution of contradictions through higher-order integration, and the generation of novel possibilities through processes that transcend classical logical constraints. As you consider your own dream experiences, notice how they often exhibit this quantum-like quality of being simultaneously meaningful and nonsensical, familiar yet impossible. Dreams don't follow the sequential logic of waking thought but seem to operate through a kind of associative coherence where connections emerge through resonance and correlation rather than linear causation. This dream logic might offer insights into how consciousness itself operates at levels deeper than ordinary waking awareness. If dreams represent consciousness freed from the constraints of sensory input and social coordination, they might reveal organizational principles that are normally hidden beneath the surface of everyday experience. One of the most intriguing aspects of both quantum mechanics and consciousness research involves the role of fields, invisible structures that seem to organize and coordinate behavior across space and time. In physics, quantum fields give rise to particles and forces through excitations and interactions that transcend simple mechanical causation. In consciousness research, similar field-like phenomena are sometimes used as metaphors to describe coordination of neural activity across different brain regions and timescales. Consider how your attention operates. When you focus on a particular object, thought, or sensation, neural activity becomes correlated across multiple brain regions in ways that seem to transcend direct anatomical connections. Neurons in visual processing areas begin synchronizing with those in memory systems, emotional centers, and motor planning regions. This coordination occurs too quickly and comprehensively to be explained through simple point-to-point neural transmission. Instead, attention appears to operate more like a field phenomenon, creating conditions where distant neural processes can achieve coherent integration without requiring direct communication pathways. This attention field exhibits properties that loosely resemble quantum fields, organizing and coordinating activity across extended regions. Through principles that remain largely mysterious, the meditation traditions have long recognized similar field-like aspects of consciousness. Advanced practitioners often describe states of awareness where the normal boundaries between self and environment, subject and object, or different sensory modalities begin to dissolve. These descriptions parallel the non-local correlations we observe in quantum entangled systems, connections that transcend ordinary spatial and temporal constraints. While we cannot scientifically claim that meditation creates quantum entanglement between brain regions, the phenomenological parallels are striking. Both quantum systems and meditative states seem to involve forms of coherence and correlation that transcend classical mechanical explanations. Both suggest that reality might be more fundamentally relational and interconnected than our everyday experience reveals. Some research has explored whether group meditation might create field effects that extend beyond individual practitioners. Studies have reported correlations between meditation practices and reduced crime rates, decreased conflict, and improved social coherence in surrounding communities. While these findings remain controversial and unconfirmed, they hint at the possibility that consciousness might have field-like properties in a metaphorical or psychological sense, even if no physical field mechanism has been scientifically demonstrated. This remains highly speculative, and no scientific consensus exists regarding such extended effects of consciousness. The brain appears to operate primarily within the confines of individual skulls, with social coordination occurring through conventional sensory and linguistic channels. Yet the possibility that consciousness might interface with more subtle environmental fields continues to inspire research at the boundaries of neuroscience and physics as a philosophical or exploratory idea rather than an established scientific fact. What's particularly intriguing is how quantum field theory itself suggests that the vacuum of space isn't empty, but filled with virtual particles and field fluctuations that exist below the threshold of direct observation. Similarly, consciousness research is revealing that awareness seems to emerge from background processes and distributed patterns of neural activity that operate below the threshold of explicit conscious experience. These parallels don't prove that consciousness operates through quantum field effects, but they suggest that both domains might be governed by similar organizational principles. Both seem to involve the emergence of definite experiences or events from fields of potentiality through processes that transcend classical mechanical causation. As you sit quietly and notice your own awareness, you might sense something of this field-like quality of consciousness. Your experience doesn't feel localized to any particular brain region, but seems to arise from the entire field of neural activity. Thoughts, sensations, and emotions don't feel like separate objects, but like waves or excitations in a unified field of awareness. This field perspective on consciousness invites a more holistic understanding of mental experience. Instead of thinking of consciousness as produced by the brain like a computer produces outputs, we might envision awareness as emerging from brain activity, like a magnetic field emerges from electric currents, a genuinely new level of organization that possesses properties not present in its underlying substrate. One of the most profound implications of quantum mechanics involves the role of observation in determining the properties of quantum systems. This observer effect doesn't require conscious awareness. Any sufficiently complex interaction can serve as a measurement, but it does suggest that the act of observation participates in creating rather than merely revealing the properties being observed. While consciousness doesn't directly create quantum effects in everyday life, there are remarkable parallels between the quantum observer effect and how attention shapes our experience of reality. When you focus awareness on particular aspects of your environment, thoughts or sensations, those elements seem to become more definite, more real, more influential in shaping your overall experience. Consider how this works with emotional states. Before you direct attention to a subtle feeling of anxiety or contentment, that emotion exists in a kind of background potentiality, present but not fully actualized in conscious experience. The act of noticing and acknowledging the emotion seems to crystallize it into more definite form, making it more real and influential in your psychological landscape. This attentional crystallization doesn't create emotions out of nothing, just as quantum measurement doesn't create particles out of nothing. Rather, it seems to actualize potentialities that were already present in latent form. The act of observation, whether quantum or psychological, appears to participate in bringing definite realities into manifestation from fields of possibility. This parallel suggests that our psychological experience of attention might operate according to principles similar to those governing quantum systems in a metaphorical sense. Both domains seem to involve the emergence of definite actualities from states of potentiality through processes that include observation or measurement as an active component rather than a passive recording of pre-existing properties. The implications extend into how we understand the relationship between subjective experience and objective reality. If attention plays an active role in crystallizing experience, then consciousness isn't simply a passive mirror reflecting an independent external world. Instead, awareness appears to participate in the ongoing creation of the reality we experience through perception, interpretation, and meaning-making, not through any physical influence over quantum systems. This doesn't mean that individual thoughts or wishes create external circumstances. Such claims would be scientifically unfounded and potentially harmful. Rather, it suggests that the quality of attention we bring to experience influences which aspects of reality become prominent in our awareness and how we interpret and respond to the circumstances we encounter. The meditation traditions have long recognized this participatory aspect of consciousness. Mindfulness practices involve learning to observe experience without immediately reacting or interpreting, allowing phenomena to arise and pass away naturally. This receptive attention seems to reveal aspects of experience that remain hidden when awareness is coloured by preconceptions or reactive patterns. Some practitioners report that sustained mindful attention reveals a more fluid, interconnected quality to experience than is apparent during ordinary consciousness. The boundaries between self and environment, between different sensory modalities, and between past and present seem less rigid and more permeable. These descriptions echo the kind of non-local correlations and boundary dissolution that characterize quantum entangled systems as a poetic comparison, not a scientific claim. While these experiential reports don't prove quantum effects in consciousness, they do suggest that different qualities of attention might reveal different aspects of reality structure. Just as different types of quantum measurements reveal complementary properties of quantum systems, different modes of conscious attention might reveal complementary aspects of the reality we inhabit. As you experiment with bringing different qualities of attention to your immediate experience, you might notice how the act of observation seems to influence what becomes apparent in awareness. Gentle, open attention might reveal subtle background sensations or emotions that focused attention would miss. Analytical attention might reveal logical relationships that receptive awareness would overlook. This suggests that consciousness possesses something analogous to the complementarity principle in quantum mechanics. Different modes of observation reveal different aspects of reality, and no single perspective captures the complete picture. The challenge, both in quantum physics and in understanding consciousness, is learning to appreciate these different perspectives as complementary rather than contradictory approaches to truth. One of the most fascinating aspects of quantum systems involves the transition between coherent and decoherent states. Quantum coherence allows particles to exist in superposition and maintain entangled correlations across space and time. But interaction with the environment gradually destroys this coherence, causing quantum systems to behave more like classical objects with definite properties and local interactions. Similar processes appear to operate in consciousness, where different states of awareness exhibit varying degrees of coherence and integration. During focused attention, neural networks achieve high levels of synchronization and correlation, creating coherent states of consciousness that feel unified and purposeful. But distraction, fatigue, and emotional turbulence can disrupt this coherence, leading to fragmented experiences where different aspects of awareness seem disconnected or conflicting. The transition between sleep and waking provides a particularly clear example of these coherence transitions in consciousness. As you fall asleep, the normally coherent networks that maintain waking awareness gradually decohere, allowing different brain regions to operate more independently. This neural decoherence creates the fragmented, illogical quality that characterizes the transition between waking and dreaming consciousness. During deep sleep, consciousness reaches its most decoherent state, with different neural networks operating in relative isolation. But as you enter REM sleep and begin dreaming, new forms of coherence emerge, different from waking coherence, but exhibiting their own patterns of integration and correlation. Dreams represent a unique coherent state where normally separate neural processes achieve novel forms of synchronization and communication. The awakening process involves a gradual recoherence of consciousness as different neural networks begin synchronizing according to the patterns that characterize normal waking awareness. This recoherence doesn't happen instantly. It's a process that can take minutes or even hours to complete fully, which explains why consciousness often feels fuzzy or fragmented immediately after waking. These natural cycles of coherence and decoherence in consciousness parallel the processes that quantum systems undergo as they interact with their environments. Both domains seem to involve dynamic transitions between states of integration and fragmentation, with different types of coherence becoming possible under different conditions. Contemplative practices appear to influence these coherence patterns in consciousness. Meditation techniques that cultivate sustained attention tend to enhance neural coherence, creating states of awareness that feel more unified, stable, and clear than ordinary waking consciousness. Advanced practitioners sometimes report achieving states of consciousness where the normal fluctuations between coherent and decoherent awareness become much more stable and integrated. Some research suggests that experienced meditators show enhanced neural coherence not only during formal practice, but also during ordinary daily activities. This enhanced baseline coherence might explain why contemplative practitioners often report feeling more integrated, purposeful, and connected to their environment than they experienced before beginning practice. These findings don't prove that meditation creates quantum effects in the brain, but they do suggest that consciousness can be trained to achieve more coherent states that loosely parallel, in a metaphorical sense, what we observe in quantum systems. Both domains seem to involve the possibility of achieving states of enhanced integration and correlation that transcend the normal constraints of classical mechanical systems. As you notice the natural fluctuations in your own awareness throughout the day, you might observe how different activities and conditions influence the coherence of consciousness. Focused creative work might enhance coherence, while multitasking or emotional stress might promote decoherence. Restful activities like walking in nature or listening to music might allow new forms of coherence to emerge that differ from the goal-directed coherence of focused attention. This suggests that consciousness, like quantum systems, might be capable of existing in multiple types of coherent states, each with its own characteristics and capabilities. Learning to recognize and cultivate different forms of coherence in awareness might be one of the most practical applications of understanding the quantum-like, but not literally quantum, properties of consciousness. One of the most challenging aspects of consciousness research involves the measurement problem. How do we study subjective experience using objective scientific methods? This challenge parallels the measurement problem in quantum mechanics, where the act of measurement seems to fundamentally alter the system being observed. In consciousness research, the very act of introspecting or reporting on mental states appears to change those states in ways that complicate scientific investigation. When you turn attention inward to observe your own thoughts or emotions, that act of observation alters the mental landscape you're trying to study. The observer becomes part of the system being observed in ways that make it difficult to separate subjective experience from the process of studying it. This isn't simply a practical limitation that better instruments might overcome. It appears to be a fundamental feature of how consciousness operates. Self-awareness seems to involve a kind of internal measurement process where consciousness observes itself, and this self-observation participates in creating the very experiences being observed, consider how this works with emotional states. When you notice that you're feeling anxious, the act of recognizing and naming that anxiety changes your relationship to the emotional experience. The anxiety doesn't remain unchanged while you observe it. It becomes something different, something observed, something that you can relate to with awareness rather than being completely identified with it. This transformation through observation parallels, in a conceptual rather than literal way, what happens in quantum measurement, where the act of measurement causes wave function, collapse, and transforms quantum superposition into definite classical states. In consciousness, the act of self-observation seemed to transform fluid, undefined inner states into more definite experiences that can be recognized, named, and related to consciously. The meditation traditions have developed sophisticated approaches to this measurement problem in consciousness. Rather than trying to observe mental states without changing them, contemplative practices work with the fact that observation necessarily transforms experience. Mindfulness meditation, for example, involves learning to observe mental phenomena in ways that promote beneficial transformations, greater clarity, reduced reactivity, enhanced equanimity. This approach recognizes that consciousness cannot be studied from a completely external perspective because awareness is always studying itself. There's no position outside consciousness from which to observe it objectively. Instead, contemplative practices develop more skillful ways of internal observation, forms of self-awareness that enhance rather than distort the natural wisdom and clarity of consciousness. Some interpretations suggest that this self-referential quality of consciousness might be fundamentally related to the observer effect in quantum mechanics. Both domains seem to involve systems that cannot be fully understood without including the process of observation as an integral component rather than an external addition to the system being studied. This doesn't mean that consciousness operates through quantum mechanisms, but it does suggest that both consciousness and quantum systems might exemplify a more general principle, that complex systems capable of self-reference or self-measurement exhibit properties that transcend classical mechanical description. The implications extend into questions about the nature of scientific knowledge itself. If consciousness is involved in all scientific observation, and if consciousness exhibits certain metaphorical, not literal quantum-like properties, then the relationship between subjective experience and objective knowledge might be more intimate than classical science assumed. This doesn't undermine the validity of scientific investigation, but it does suggest that science might benefit from developing more sophisticated approaches to studying systems that include consciousness as an integral component. The contemplative traditions offer thousands of years of systematic investigation into the nature of consciousness using first-person methodologies that complement third-person scientific approaches. As you reflect on your own experience of self-observation, you might notice how the act of watching thoughts and emotions seems to create space around those experiences. They become phenomena arising in awareness rather than defining your entire reality. This spaciousness created through conscious observation might be similar to how quantum measurement creates definite outcomes from indefinite potentialities, again, as a metaphor for clarity rather than a literal quantum effect. Both processes seem to involve the emergence of clarity and definiteness through the participation of observation. One of the most striking aspects of both quantum entanglement and consciousness involves how individual elements become connected in networks that exhibit emergent properties not present in isolated components. In quantum systems, entangled particles form correlational networks where the state of the entire system cannot be reduced to the states of individual particles. In consciousness, thoughts, emotions, memories, and sensations form networks of meaning where the significance of individual elements emerges through their relationships within larger patterns. Consider how meaning emerges in language. Individual words don't carry fixed meanings in isolation. Their significance arises through relationships with other words, in sentences, paragraphs, and larger linguistic contexts. Similarly, individual thoughts or experiences don't carry fixed significance, but derive their meaning through relationships with other elements in the network of consciousness. This relational nature of meaning parallels the relational nature of quantum entanglement, where individual particles don't possess definite properties in isolation, but only in relation to the larger quantum system they participate in. Both domains seem to involve forms of organization where relationships are more fundamental than the individual elements being related. Recent neuroscience research has revealed that the brain operates as a complex network where meaning emerges through patterns of connectivity rather than the activity of individual neurons. Neural networks that process language, memory, emotion, and sensory information become dynamically linked in ways that create unified experiences of meaning from distributed information processing. These neural networks exhibit properties similar to quantum entangled systems. Changes in one part of the network can instantly influence distant parts through correlations that transcend direct anatomical connections. The brain seems to operate more like an integrated information field than a collection of separate processing modules, with meaning emerging from the coherent patterns that span multiple network components. This network perspective on consciousness helps explain how complex meanings can emerge so quickly in awareness. When you recognize a friend's face, understand a joke, or grasp the significance of a piece of music, meaning doesn't build up gradually through sequential processing. Instead, it seems to emerge instantaneously through the activation of entire networks of associated memories, emotions, and conceptual relationships. The speed and comprehensiveness of this meaning emergence suggests processes that transcend classical information processing. Like quantum entanglement, conscious meaning-making seems to involve forms of correlation and integration that operate outside normal, temporal, and spatial constraints as a psychological description, not a claim of literal quantum physics. Contemplative practices work directly with these networks of meaning in consciousness. Meditation often involves observing how thoughts, emotions, and sensations arise not as isolated phenomena, but as interconnected patterns that reflect deeper structures of meaning and association. Advanced practitioners sometimes report states where the normal networks of conceptual meaning dissolve, revealing more fundamental levels of consciousness that exist prior to the construction of specific meanings. These experiences don't prove quantum effects in consciousness, but they do suggest that awareness might operate at multiple levels of organization, from the conceptual networks that create specific meanings to more fundamental levels where consciousness exists as pure potentiality prior to the crystallization of particular experiences. As you observe your own mental experience, you might notice how individual thoughts rarely occur in isolation, but tend to activate entire clusters of related memories, associations, and emotional responses. This clustering suggests that consciousness operates more like an integrated network than a sequential processor, with meaning emerging through patterns of relationship rather than linear chains of cause and effect. This network perspective has practical implications for understanding how consciousness can be transformed through contemplative practice. Rather than trying to change specific thoughts or emotions in isolation, effective practices often work with entire networks of meaning, allowing new patterns of connection to emerge that transform the significance of individual experiences. Some research suggests that psychedelic experiences, which often produce profound shifts in consciousness, might work by temporarily disrupting normal networks of meaning and allowing new patterns of connectivity to emerge. This network reorganization might explain why such experiences often produce lasting changes in perspective and understanding that persist long after the acute effects have ended. If you enjoyed drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. As we approach the boundaries of current scientific understanding, the parallels between quantum mechanics and consciousness become both more intriguing and more speculative. We're entering territory where rigorous science meets profound mystery, where the questions become more important than definitive answers, and where the act of inquiry itself transforms our relationship to the phenomena we're investigating. One of the most fascinating frontiers involves the possibility that consciousness might interface with quantum processes in ways that remain largely undetected by current scientific instruments. While the brain appears to operate primarily through classical neural mechanisms, some researchers are investigating whether quantum effects might play subtle but important roles in neural computation, memory formation, or the integration of conscious experience. These investigations remain highly speculative, and no scientific consensus exists regarding quantum effects in consciousness. The warm, noisy environment of biological tissue would quickly destroy most quantum coherence, making large-scale quantum effects in the brain unlikely. Yet the possibility persists that biological systems might have evolved ways to protect and utilize quantum effects in specialized cellular structures or molecular processes. Some theoretical work has explored whether quantum effects might contribute to the hard problem of consciousness, explaining how subjective experience arises from objective neural processes. According to some interpretations, quantum mechanics might provide a bridge between the physical and experiential aspects of reality by revealing that observation and measurement play fundamental roles in determining the properties of quantum systems. This doesn't mean that consciousness creates reality through wishful thinking. Such claims would be scientifically unfounded and potentially harmful. Rather, it suggests that the relationship between subjective experience and objective reality might be more intimate and participatory than classical science assumed, with observation playing an active rather than passive role in the unfolding of experience itself in a psychological, not physics-based sense. These questions don't demand immediate answers, but they invite us to consider possibilities that extend beyond the boundaries of current scientific paradigms. In a universe where quantum entanglement reveals genuinely non-local correlations, where measurement participates in creating rather than merely revealing reality, and where wholeness transcends spatial separation, there's room for wonder about aspects of existence that classical science never imagined. Perhaps the most profound recognition emerging from quantum mechanics involves the fundamental interconnectedness of reality. If entangled particles maintain instant correlations regardless of distance, if quantum fields underlie all matter and energy, and if observation plays an active role in determining the properties of quantum systems, then the classical picture of reality as composed of separate, independent objects begins to dissolve. This doesn't mean that boundaries and distinctions are illusory. Your coffee cup remains distinct from your kitchen table in practical terms. Rather, it suggests that these apparent separations emerge from more fundamental levels of connection and correlation. The universe begins to look less like a collection of isolated objects and more like a vast network of relationships, with individual entities arising as local manifestations of deeper patterns of organization. As you contemplate this vision of reality, notice how it might resonate with your own deepest experiences of connection and belonging. While we cannot scientifically claim that human relationships operate through quantum mechanisms, the recognition that reality itself may be fundamentally relational rather than mechanical opens space for appreciating the mysterious ways we find ourselves connected to others, to nature, and to the cosmos itself. Some interpretations of quantum mechanics suggest that information might be more fundamental than matter or energy, with particles, forces, and fields representing different ways that information organizes itself into the patterns we experience as physical reality. If consciousness is intimately connected with the processing and integration of information, this informational view of reality might offer metaphorical, not literal, perspectives on the relationship between mind and matter. These remain speculative ideas rather than established scientific facts, but they illustrate how quantum mechanics continues to challenge our fundamental assumptions about the nature of existence. Each new discovery in quantum physics seems to reveal that reality is stranger, more subtle, and more interconnected than previous generations ever imagined. The practical implications continue to unfold in research laboratories and technology companies around the world. Quantum computers are beginning to solve problems that would be impossible for classical machines. Quantum communication networks are creating unbreakably secure channels for transmitting information. Quantum sensors are achieving measurement precision that approaches fundamental physical limits. But perhaps the most significant impact of quantum entanglement lies not in specific technologies, but in how it has expanded our conception of what's possible, in revealing that nature operates according to principles that transcend classical logic and intuition. Quantum mechanics has opened intellectual territories that were previously unimaginable. This expansion of possibility extends beyond physics into questions about consciousness, meaning, and our place in the cosmos. If reality is fundamentally non-local and relational, if observation participates in creating experience, and if wholeness transcends apparent separation, then many aspects of human existence that seemed mysterious or supernatural, from a classical perspective, can be explored metaphorically without implying literal quantum causation. Take a moment to consider how quantum entanglement might influence your understanding of your own life and relationships. While individual thoughts and emotions don't directly create quantum effects, the recognition that reality itself is fundamentally interconnected might offer new perspectives on the nature of love, empathy, intuition, and the mysterious ways we sometimes feel connected to others across space and time. These connections might not operate through literal quantum entanglement, but they might reflect loosely analogous organizational principles, forms of correlation and coherence that transcend simple mechanical explanations. The quantum world's revelation that wholeness can transcend spatial separation invites us to consider whether aspects of human experience might operate according to similar principles of non-local connection and emergent unity in a poetic sense. As our exploration draws toward its natural conclusion, it's worth stepping back to appreciate the extraordinary journey we've taken together. We began with Einstein's discomfort about spooky action at a distance, and have travelled through experimental confirmations, technological applications, philosophical implications, and speculative connections to consciousness that reveal quantum entanglement to be far more than just another curious physical phenomenon. What makes quantum entanglement so remarkable isn't just its strangeness, but its accessibility to wonder. Unlike many advanced scientific concepts that require years of specialized study to appreciate, the mystery of non-local correlation speaks to something immediate in human experience. Our intuitive sense that the universe might be more interconnected and meaningful than classical physics suggested. The mathematics may be complex and the experiments may require sophisticated equipment, but the fundamental questions raised by entanglement touch the deepest concerns of human existence. How are we connected to each other and to the world? What is the nature of reality beyond appearance? How does consciousness relate to the physical universe? What does it mean to be part of something larger than ourselves? Quantum entanglement doesn't answer these questions definitively, but it does reveal that the universe is far more mysterious, interconnected, and wonderful than our everyday experience typically suggests. In a cosmos where distant particles can share immediate correlations, where measurement participates in creating rather than merely revealing reality, and where wholeness transcends spatial separation, there's room for forms of meaning and connection that classical science never imagined. This recognition invites a particular kind of intellectual humility. If nature operates according to principles that challenge our deepest intuitions about space, time, and causation, how many other aspects of reality might be far stranger and more wonderful than we currently imagine? What other discoveries await that will expand our understanding of what's possible in this remarkable universe we call home? The story of quantum entanglement also reveals something beautiful about the nature of scientific discovery itself. The greatest breakthroughs often emerge not from confirming what we expect, but from encountering phenomena that challenge our fundamental assumptions about how reality works. Einstein's discomfort with quantum non-locality wasn't a failure of imagination. It was the natural response of a brilliant mind encountering evidence that the universe operates in ways that transcend classical categories of thought. The experimental confirmation of quantum entanglement represents one of the most profound victories of human curiosity over preconception. Through patient observation, rigorous experimentation, and mathematical precision, scientists have revealed aspects of reality that no amount of pure reasoning could have anticipated. The universe has shown itself to be far more creative and mysterious than even our boldest theories suggested. As these discoveries continue to unfold, they're not only advancing our scientific understanding, but also expanding our sense of what it means to exist in this cosmos. We're not isolated observers studying a mechanical universe from the outside. We're participants in a reality that exhibits forms of correlation, coherence, and connection that extend far beyond anything classical physics ever imagined. The technological applications of quantum entanglement are already beginning to transform how we compute, communicate, and measure the world around us. But perhaps the deeper transformation involves how these discoveries change our relationship to mystery itself. In recognizing that the deepest truths about reality often emerge through accepting rather than resolving paradox, we learn to dance more gracefully with the questions that expand rather than constrain our sense of wonder. Some interpretations suggest that quantum entanglement might offer glimpses into organizational principles that operate throughout nature, from the coordination of neural networks in consciousness to the emergence of coherent patterns in complex systems. While these connections remain speculative, they hint at the possibility that the non-local correlations revealed by quantum mechanics might reflect broad patterns of organization rather than direct causal links. As you reflect on your own experience of connection and correlation in daily life, you might notice subtle parallels with the quantum world's revelation of non-local relationship. The way attention can instantly shift awareness across different aspects of experience. The way meaning emerges through patterns of association that transcend linear causation. The way consciousness seems to exhibit forms of coherence and integration that transcend simple mechanical explanation. These experiential parallels don't prove quantum effects in consciousness, but they do suggest that both domains might exemplify similar organizational principles, forms of wholeness and correlation that transcend classical mechanical description in a metaphorical sense. This recognition invites a more nuanced understanding of the relationship between scientific discovery and personal experience, between objective knowledge and subjective meaning. The contemplative traditions have long recognized forms of interconnection and non-local correlation in consciousness that parallel what physicists observe in quantum systems. Advanced meditation practitioners often describe states of awareness where the normal boundaries between self and environment, between different aspects of experience, seem to dissolve into more fundamental forms of unity and coherence. While these experiential reports don't constitute scientific evidence for quantum effects in consciousness, they do suggest that human awareness might be capable of recognizing forms of connection and wholeness that transcend ordinary conceptual categories. The dialogue between quantum physics and contemplative practice continues to reveal unexpected convergences between scientific discovery and direct investigation of consciousness. Perhaps the greatest gift of quantum entanglement lies not in any specific technological application or theoretical insight, but in how it has expanded our capacity for wonder about the nature of existence itself. In revealing that reality transcends our classical categories of thought, quantum mechanics invites us into a more open, curious, and appreciative relationship with the mystery in which we find ourselves immersed. This doesn't diminish the importance of rigorous scientific investigation or careful philosophical analysis. Rather, it suggests that the deepest truths about reality might emerge through combining precise observation with open-minded wonder, mathematical rigor with poetic imagination, experimental confirmation with contemplative insight. As we move forward into an era where quantum technologies are beginning to reshape human civilization, these broader implications of quantum entanglement become increasingly relevant. We're not just developing new tools and techniques, we're discovering new ways of understanding our place in a universe that is far more interconnected, meaningful, and mysterious than previous generations ever imagined. The recognition that reality operates according to principles of non-local correlation and emergent wholeness offers new perspectives on ancient questions about the nature of existence, consciousness, and our relationship to the cosmos. While science cannot provide final answers to these ultimate questions, it can reveal aspects of reality that expand rather than constrain our sense of what might be possible. In this spirit, quantum entanglement becomes more than just another chapter in the history of physics. It represents an invitation to expand our conception of reality, to embrace forms of mystery that enhance rather than diminish our appreciation for existence, and to recognize that we're part of a universe that is far more wonderful and interconnected than our everyday experience typically reveals. As we close this gentle exploration together, take a moment to appreciate how quantum entanglement has opened new territories of wonder that extend far beyond the boundaries of any single scientific discipline. These discoveries don't provide final answers, but rather invite us into deeper questions about the nature of connection, consciousness, and the remarkable cosmos we inhabit. The story of quantum entanglement continues to unfold in research laboratories and contemplative practices around the world. Each new discovery adds layers to our understanding, while simultaneously revealing new depths of mystery. This isn't a limitation of our scientific methods, but a testament to the inexhaustible richness of reality itself. Thank you for joining me on this journey through one of nature's most beautiful and profound mysteries. The universe has revealed itself to be far stranger, more interconnected, and more wonderful than Einstein's classical intuition suggested, while simultaneously honouring his demand for experimental rigour and mathematical precision. If you enjoyed drifting through these explorations, consider how the mysterious connections we've discovered in the quantum realm might manifest in the landscape of sleep and consciousness. Until we meet again in that realm of questions that expand rather than constrain our sense of wonder, may you carry with you a deepened appreciation for the profound interconnectedness that quantum entanglement reveals at the very heart of reality. If you found yourself drawn into these mysteries of quantum connection and consciousness, I invite you to continue this exploration with Quantum Dreams, the hidden code your subconscious is desperate to reveal, where we'll discover how the strange principles we've explored tonight might manifest in the landscape of sleep and dreams, framed metaphorically and scientifically responsibly, revealing hidden patterns that connect the quantum world to the deepest levels of human awareness. The quantum realm reaches into the world of biology in ways that continue to astonish researchers. From the navigation systems of migratory birds to the efficiency of photosynthesis in plants, nature appears to have discovered how to make use of certain quantum effects under biological conditions long before humans conceived of quantum mechanics. These discoveries suggest that the strange principles we've explored aren't confined to laboratory experiments. They may be woven into the very fabric of life itself in ways that are still being researched and debated. Consider the remarkable case of the European robin. Twice each year, these small birds navigate thousands of miles with pinpoint accuracy, travelling from Scandinavia to North Africa and back again without GPS, landmarks, or any external guidance system we can detect. For decades, scientists puzzled over how such tiny creatures could accomplish such extraordinary feats of navigation. Recent research suggests an answer so elegant it borders on poetry. Inside the robin's eye, there appears to be a protein called cryptochrome that may support delicate quantum reactions, potentially involving pairs of electrons whose spin states are sensitive to Earth's magnetic field. The bird may, in effect, perceive magnetic information in a way that helps guide its remarkable journeys, a hypothesis still under active investigation. What makes this discovery particularly fascinating is that these quantum effects appear to persist in the warm, noisy environment of a living organism, conditions that would normally destroy quantum coherence almost instantly. Yet somehow, evolution may have found ways to protect and utilize these delicate quantum states for biological purposes. The robin's navigation system represents a form of quantum-enhanced biology that scientists are still working to understand, rather than a fully confirmed mechanism. As you contemplate this possibility, imagine looking up at the night sky and seeing not just stars and darkness, but invisible highways of magnetic force stretching across the heavens. This may be closer to the actual experience of a migrating bird than our human perception suggests. The quantum world doesn't just exist in abstract mathematics. It may, in carefully limited and well-protected ways, be part of the lived reality of countless creatures sharing our planet. But birds aren't the only organisms that may exploit quantum effects. Photosynthesis, the process by which plants convert sunlight into chemical energy, operates with an efficiency that classical physics struggles to explain. When light hits a chlorophyll molecule, the resulting energy doesn't simply bounce randomly from molecule to molecule until it reaches a reaction center. Instead, it appears, based on current research, to explore multiple pathways simultaneously, finding the most efficient route through what researchers describe as quantum coherence. This process resembles a quantum computer performing a complex optimization calculation. The energy exists in superposition, taking all possible paths at once, then somehow selecting the optimal route to its destination. This quantum-like enhanced efficiency helps explain why photosynthesis can operate effectively, even in the dim, scattered light of forest understories or cloudy days. The implications stretch far beyond botany. If plants have been using quantum-influenced processes for photosynthesis over billions of years, what might this teach us about designing more efficient solar panels or energy storage systems? Some researchers are already exploring biomimetic approaches that attempt to replicate nature's quantum-inspired energy transfer in artificial systems. These discoveries in quantum biology raise profound questions about the role of quantum effects in living systems. If birds may maintain quantum coherence for navigation, and plants can use quantum coherence for energy transfer, what other biological processes might rely on quantum mechanics? Could quantum effects play roles in enzyme function, cellular signaling, or even the operation of the nervous system? The answers remain largely speculative, but early research has identified possible quantum effects in various biological contexts. Some enzymes appear to use quantum tunneling to accelerate chemical reactions. Certain cellular processes show signatures of quantum coherence that persist far longer than classical physics would predict. Even the sense of smell may involve quantum effects, with molecules distinguished not just by their shape, but by their vibrational frequencies through quantum tunneling processes in olfactory receptors. Take a moment to consider your own relationship with the natural world in light of these discoveries. The trees around you may be conducting quantum-influenced energy pathways with every photon they absorb. The birds overhead may be navigating by quantum-sensitive biochemical reactions. Even your ability to detect subtle fragrances may involve quantum tunneling in your nasal receptors. The quantum world isn't separate from the biological world. It may be one of its fundamental operating principles in specific still-studied cases. This recognition transforms our understanding of evolution itself. Natural selection hasn't just shaped organisms through classical mechanical processes of survival and reproduction. It has also discovered ways to harness the subtle quantum properties of matter and energy, creating biological systems that operate according to principles we're only beginning to understand. The elegance of these quantum biological systems offers inspiration for developing new technologies. Quantum sensors inspired by bird navigation could revolutionize precision measurement. energy transfer systems based on photosynthetic quantum coherence might lead to dramatically more efficient solar power. Understanding how biological systems protect quantum effects from environmental interference could solve some of the greatest challenges in quantum computing and communication. But perhaps the most profound implication involves recognizing that the boundary between the quantum and classical worlds isn't as clear as once believed. Life exists at the interface between these realms, somehow managing to preserve and utilize quantum effects while operating in the warm, noisy conditions that characterize biological systems. This interface suggests that consciousness itself, as a biological phenomenon, might exist at the crossroads between quantum and classical physics. While this remains highly speculative and no scientific consensus exists regarding quantum effects in consciousness, the discovery of quantum processes in other biological systems opens new questions about how awareness might emerge from the complex interplay between quantum and classical processes in the brain.